Okay, we are going to talk about the infinite sequences and series. We start with the sequences first. You can consider sequences as numbers on the real line, and you can express them you can express them by using some compact form, like for example an is equal to square root of n. As n changes, for n is equal to 1 you get 1, for n equals to 2 you have square root of 2, for n is equal to 3 you have square root of 3, etc. You can express them compactly here. Okay, and also you can draw the graph of them as well, like this. For n you have the corresponding an drawn up here. An is equal to 1 over n is also similarly this compact form. For n is equal to 1 it's 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. And there's another an here, sequence. An negative 1 to the n plus 1, 1 over n. For n is equal to 1, this is positive 1. For n is equal to 2, negative 1 over 2. See, a2 is negative 1 over 2. a3 is 1 over 3. a4 is negative 1 over 4. a5 is 1 over 5. So you have this distributed to the right and to the left of 0. This is an. You can also see it on this graph. Look, this is the x-axis or n-axis. We have 1, negative 1 over 2, 1 over 3, negative 1 over 4, and 1 over 5. You can see them like in here as well. So we are interested in where these ANs goes to, get close to. Alright. So there's an L limit. We consider that this, if infinitely many of such ANs lives close by this L, then we call this L to be the limit. See, only finitely many are outside of this neighborhood. Okay, that's called the limit. Or you can say, if this is L, look, infinitely many of them are living in here, only finitely many are in here. Okay, because as n goes to infinity we have more and more in here. So this is called the limit. A sequence can converge or not, or diverge depending on its situation. Let's see, and there's an unbounded sequence as well. We are gonna say a sequence is a sequence an diverges to infinity if for every m there is an n such that for all n larger than n, an is greater than m. So there's no way you can stop it. So if you try to say, oh, this is the last element, or this is the biggest value that it can take, there's always another point bigger than that. So that sequence is going to go to infinity as n goes to infinity, as n approaches to infinity, right? That's why what it's called diverge to infinity. Sometimes they may diverge to negative infinity as well. So for that we can understand it like this. The numbers, sometimes we'll say, okay, this is the smallest number it can take, this sequence, but you will be always able to find another negative number in the sequence less than that. So there's no end to it. This is when we have it, we get this negative infinity diverging to a negative infinity situation. There are some rules with the sequences. You can consider them as functions. Functions, we can add them, subtract them, take the ratio, multiply them, etc. You can also do that with the sequences as well. Let's say an and b and b sequence of real numbers, and let's a and b be the real numbers such that they are the limits of these sequences. Limit of an is a, limit of bn is b. The sum limit of the sequence of an and bn is equal to sum of the limits. Limit of the differences of the sequences is the differences of the limits. Limit of the k times the sequence is going to be equal to k times the limit of the sequence. Limit of the an times bn is going to be the product of the limits. Limit of the ratio of the sequences is the ratios of the limits, as long as b is not a zero number. Okay, sometimes we have the sandwich theorem like for functions, but we already have the sandwich theorem for functions, but we have a similar sandwich theorem for sequences as well. So let's consider we have 3 sequences here, a n, b n, c n. They are a sequence of real numbers, and a n less than or equal to b n less than or equal to c n for all n beyond some index, which means after some finitely many numbers they are following that rule. And let's say an and bn has the same limits, L, then bn, which is in between, squeezed in between, sandwiched in between, is going to have the same limit. Look at the picture here. An and cn, bn is squeezed between an and cn, the numbers in between. Cn and an, we know that they go to L, so bn has to go to L because of that. Okay, and we have a continuous function theorem for sequences. Let's say n is a sequence of real numbers and an has a limit L, and we have a function that's continuous function at the point L. Then f of an is going to go to the f of L. So as long as f is continuous, you can do that. Let's see that. For example, this is a nice example. Let's consider 1 over n. This is an an. An is going to go to 0, right? An goes to 0, we know. And let's consider 2 to the x function. 2 to the x function is like this. 2 to the x function is a continuous function. It has no discontinuity, is nothing. It's a very nice function. And if this is f of x, f of 1 over n is going to go to f of 0. This is f of 1 over n. F of 1 over n is going to go to f of 0 because f is a continuous function. It follows this theorem. F of 0, 2 to the 0 is 1, so we are going to say 2 to the 1 over n sequence, this new sequence is going to go to 1 because of that. Look at that, f of x is 2 to the x here. Okay? Let's see. Actually, yeah, this is a little bit different. Let's say f of x is a function defined for all x greater or equal to n0, and an is a sequence of real numbers such that actually an is equal to f of n for n greater or equal to n0. Then an goes to 0 whenever the limit of f is L. Okay, if you know the limit of f, then the sequence is going to go to the same number because the sequence is made up of from the function. If the function goes to the limit L, then the sequence is going to go to that value as well. Let's look at these limits. Look at that limit ln n over n. You can consider this as f of x over, you can consider f of x as ln x over x. F of x is equal to ln x over x is going to go to 0 because of you can use the L'Hopital's rule, apply L'Hopital's rule, and you're going to get 0. So since this sequence is a part of that f of x, then this is going to go to the same function because of the theorem we have seen. For example, let's say here we have x, so it's kind of confusing for us. Consider x an arbitrary number, let's say 2 to the 1 over n, right? Consider f of x as 2 to the x, alright? So 2 to the x is a continuous function, so 2 to the 1 over n, 2 to the 1 over n is going to go to, 2 to the x as x approaches to infinity. I'm sorry, just 2 to the 1 over x, 2 to the 1 over x, we should say. 2 to the 1 over x is going to go to 2 to the 0, which is 1. Because of that, this function, this expression is going to go to 1 as well. We can solve it by using the theorems we have used. And number 2, nth root of n in this case. This is the nth root of n. Maybe we can take the logarithm 1 over n, right? Logarithm n. This is similar to this. We know this goes to 0. Then you take the exponential of that. Exponential is going to go to 1. You can get it from here. You're going to combine two facts we have used. Function being continuous and the fact we had here. And you get that, okay? And x to the n, x is less than 1. As an example, take x is equal to 1 over 2, 1 over 2 to the n. Consider the function, let's take x as a, otherwise you get confused. Okay, f of x is equal to a to the x. Okay, a to the x, whenever a is less than 1, okay, as x goes to infinity, this is going to go to 0, we know that. So, this is the same story here. Let's get 5. For 5, we have to use the logarithm. N log of this. Okay, n log. If you take, let's call this y. And take the logarithm. Logarithm y is equal to n logarithm 1 plus x over n. Alright. Consider n as a number that's right. Call it as n goes to infinity, what do we have? Logarithm 1 plus 0, okay, 1 plus 0 with logarithm 1, and then n outside, but we can write, I need a piece of paper to explain this to you, so you can just memorize that, okay? And also memorize this one too. Alright, so we have a notion of sequences being bounded above from a number and bounded below from a number. We have least upper bound notion, greatest lower bound notion, and unbounded notion. As you see, this sequence is bounded between capital M and M. It doesn't go outside of this border, okay? It doesn't have a limit, but it just lives in between these two numbers, the values of the sequence. But we've seen the unbounded sequence before. Like the functions, we have non-decreasing, in other words, increasing sequence, decreasing sequence, or non-decreasing, non-increasing sequence, okay? We have all that. We call it monotonic when we have either one, either non-decreasing or non-increasing. Non-decreasing means it's not going to decrease, okay? So it's going to always increase. Non-increasing means it's going to always decrease. It's not going to increase, okay? We have a monotonic sequence theorem. If you have a sequence and both bounded and monotonic, then for sure it is going to converge. Which means if the function, let's say, increasing and it's bounded, it's going to increase, but there's a bound, definitely it's going to converge. Or if you have a sequence that's going to increase, but there's a bound from the below, if we expect that it's convergent. Like in here. So this sequence actually, after some point, after n, it lives in this neighborhood. We have an upper bound, and it's increasing, by the way. This non-decreasing sequence means it's increasing, and there's an upper bound, so we expect that it has a limit.